Welcome to the lecture on heat treatment of non-ferrous metals and alloys. So, whatever heat treatment processes we discussed so far, they were normally suitable with respect to steel, and in most of the cases we have taken these eutectoid transformation into picture. We were going to the austenitizing temperature, then from there we were quenching using different mode, maybe by air quenching or oil quenching, or maybe annealing or so. Now, you have the presence of non-ferrous metals and alloys also, which are very much a part of essential part of the materials used for engineering purposes. And there also you have the heat treatment processes to be employed, so that you can attain the desired properties in those materials. So, when we talk about the principles of the heat treatment in those materials, again we are going to have certain discussions on how the how that strengthening is achieved, that we have studied a little bit. But what are those different methods by which you can think of increasing the strength of the material by adopting the suitable heat treatment method. So, the principle which govern the heat treatment of metals and alloys, they are applicable to both ferrous and non-ferrous alloys. So, in fact the principle will be same. There also you would like to have the heat treatment in such a manner that there will be diffusion of atom taking place, or there may be strengthening because of other strengthening mechanisms, like there may be cold working, so that followed by annealing and all that. So, that is so certainly there are certain changes. So, in practice there will be some sufficient differences when we talk about the non-ferrous materials, because when we talk about the ferrous materials, so we are mostly concerned with the eutectoid transformation, or we are concerned with the Martensitic transformation, which gives the hard phase, which increases the properties of the material. However, that will not very frequently be encountered when we talk about the heat treatment of non-ferrous materials and alloys. So, in this however, chemical homogenization is the one of cast structure which is there for most of the materials, whether it is the ferrous or non-ferrous. The chemical homogeneity of the cast structure is always important, and that we try to achieve by using the suitable heat treatment method. So, the principles followed for the heat treatment of non-ferrous alloys, they are normally either one is by diffusion. So, how there will be diffusion, mostly because of the solute diffusion, and they will go into the different places and strengthening the matrix, and so and that also because that will be varying with temperature. So, certainly that is one of the process. Apart from that, we have annealing after cold working, that we will discuss, because many a times when we do the cold working, so we need to have the annealing process in place. So, that is the one. Then you have homogenization annealing, then precipitation hardening. All these practices are adopted, and they are mostly used heat treatment processes for non-ferrous materials. So, if you talk about the annealing, so if you see that if you go for the annealing of cold worked structure, so in that case what we see is that when we go for cold working, so many a times, because when we have to have the geometry or the final shape which is the cold work product. So, in that case you want that in one go you should be able to get that shape, but that becomes very difficult. And for that what happens, that is the limitation is the hardness which is increasing as you increase the degree of cold work. So, so what happens that in that case you have to have the proper heat treatment, so that because once you go for cold working you are basically reducing the size in one dimension, and certainly there will be change of dimension in other directions. So, basically you are reducing the thickness, and accordingly since there is plastic deformation, so you will have the strain hardening taking place. And because of that the further up to certain extent you can go for the reduction in the dimension or the thickness, but after that the material may crack, it may be unsuitable for the use. So, in those cases what we do is we we give certain heat treatment process that is annealing prior to reaching this limit that. So that basically will be restoring the metal or alloy to a structural condition which will be similar to that prior to deformation. So, and then additional cold working can be further conducted. So, what happens that when we go for such heat treatment processes, then certainly we come across the different stages in which through which the material undergoes, and these stages are basically depending upon the temperature. So, initially you have the recovery zone, then you have the recrystallization zone, and then you have grain growth zone. So, all these zones are encountered in such cases. So, when you if you talk about the annealing of the cold worked crystal, so normally so in the case of non-ferrous materials and alloys, you have the small components which are made, or you have thin because they have they are used as the finished products. So, you have smaller dimensions of products, and then so what you do is you do the cold working, and as we know that when we go on cold working the material, so the dislocation density will increase. We all know that how these because because of the dislocation you need the smaller stress level to plastically deform. So that is what so they are basically dislocations are playing a very important role in fact in plastic deformation, because they will be reducing that energy which is required for the deformation by slip. So, we know that this deformation is either by slip or by twin. So, so that way your deformation starts. So, because of these presence of these dislocations. Now, what happens that so after a certain limit, then when the dislocation density has become quite high, in that case what we do is we try to further anneal the material. By doing this annealing process, the material becomes soft, and then further you can do the plastic deformation of the material, because at one point of time it becomes difficult. So, you can further go for the plastic deformation. So, So, accordingly this process of that treatment which is given, so that the metal can further be subjected to the plastic deformation, that process is the annealing process. So, if we recall that how this cold working affects the mechanical properties, we have already seen that if you go for the reduction in thickness, then if the reduction in thickness is there, if it is percentage, so suppose 10, 20, 30, 40, 50 and 60. So, suppose 10, 20, 30, 40, 50 and 60. So, in that case, if you take for the copper zinc solid solution, so for that your depending upon the zinc percentage, so what we see that there will be change in the hardness. So, if the hardness is there, so if you increase the reduction percentage in thickness, so your hardness will increase. So, that will be for the copper and 20 zinc percentage. So it starts from 125 hardness and one HRB, and then it goes towards this range, maybe close to 190 or so. So, similarly for different so what happens that in the case of annealing, your strength is increasing. So, if you take in general the variation of the properties, so if you take the reduction in area percentage, and if it is say 20, 40, 60 and 80. So, if you look at the variation of the properties, what you see is your tensile strength will vary like this. Similarly, your yield strength will also have some variation. Then hardness more typically varies like this, but the elongation will normally be going on decreasing. So, your tensile strength and yield strength and hardness, and this is your elongation. So, elongation is decreasing. So, what you do is normally you go for the annealing, and in annealing you are taking a temperature. So, suppose for the copper 5Zn alloy, if you go do the annealing, so annealing will be done, and if you in annealing normally you have the time is very important for how much time you are doing the annealing, and also the temperature. So, if you keep the temperature to maybe 400 degrees centigrade, in that case what we seen is that the hardness has variation, and hardness will be decreasing, and ultimately it will follow like this, and then ultimately you will have somewhat constant after some time. So, if the time is taken in terms of hour, so what was seen is that this is time of 20 hours, and then you have this as 40 hours. This is so this way it moves, and in this case normally you have what you see is in the in this zone you have so up to this this stays in this zone. So, this zone will be for the for recovery, and then this particular zone this zone will be closed for this recrystallization, and further in the third stage you have the grain growth which starts appearing in this zone. So, you will have zones identified, you will have recovery here, then you have this is the recrystallization, and then further you have the grain growth, and once there is grain growth taking place, in that case you will have the property, as you see the hardness becomes quite less. So that way with the with the process of recovery. Recovery means basically what you do in these cases, that your strained crystals are converted to strain free crystals. So, initially that recovery process takes place, then you have the decrystallization, the birth of new crystals in those zones where so, and then further after, if you prolong it, so there is a chance of having grain growth. So, that also depends upon the temperature. If your temperature is higher, then and you are holding for larger time, in that case there is certainly some chance for the grain growth to take place. So, so you will be taking suitably the temperature, and then you are keeping for some time, so that the material induces this hardness is decreased, and in this stage you have the formation of new grains. So, you will have there will be fineness and if you stop towards this side. So, depending upon the temperature, basically these these stages are observed in the case of the annealing treatment. Next thing which is important in the case of these non-ferrous materials is the homogenization of casting. Now, if you talk about the need for the homogenization of the cast structure, so typically for the alloys, when we go for the solidification of alloys, in that case we do not have the homogenized structure, we do not have the chemical composition uniform in the crystal when you are casting. When you have, if you talk about the as cast structure, then the structure is not completely homogeneous chemically. Now, because of that the one of the phenomena that is coring, that is experienced, and that can be understood by looking at the phase diagrams. If you look at the simple binary phase diagram for an alloy, so if you look at this kind of so this is going here, and then this is your. Now, what happens that if you look at the freezing mechanism for such alloys, if your percentage of B is going like this, you have A 100% here and B 100% here. So, what happens that when you try to so this is your liquid, and this is liquid plus solid, and this is your solid. Now, what happens that when the temperature is here, you are in liquid state. When the temperature comes down, you are coming here, and at this point there is so now once the temperature goes behind this below this temperature, then there will be solidification starting. So, at this point the solid which will be crystallizing out, so it will have this composition. Actually, this will be the composition of this solid which will be crystallizing out. So, initially in the core of the crystal, the solidified part which is getting solidified, it has some composition, maybe like 5% of B is there. Now, as you go as the temperature is decreasing, so if you look at if the temperature is decreased, so at this point suppose when if you see the solid which is formed, that will have the composition that will be by this. So, it will come to suppose say 10%. So, like that, as the temperature comes down, then in that case the concentration of the solute in the solidified crystal, that portion at that moment of time will be changing. So, this leads to, so if you look at the concentration of the solute or percentage of B in that crystal. So, initially you will have very small amount of B, and then that goes on increasing. So what you see, so that can be seen when you etch, then that is visible, and this is basically the chemical inhomogeneity which is present, and which is very much because and very much a trait of such alloys when you are cooling fast, because if the cooling is slow, in that case there will be sufficient time for the diffusion to redistribute the movement of atoms, so that as you go towards the end. So, if you suppose you are coming towards the end, at that point of time, this will be at this point this will be the concentration of solute, this is the concentration of B, the solid crystal which has come out, and the liquid has this concentration. So, the thing is that when you go for the cooling, that too in a fast manner, which is normally in normal case the cooling is not the equilibrium type of cooling, which is normally extremely slow, but when you go for fast cooling, so you are not giving enough time for the atoms to redistribute or to diffuse, so that you have proper chemical homogenization. So, your you have chemical inhomogeneity which is present, and this difference concentration difference which is caused, that is that leads to the process known as coring. So, basically we also know that normally when you go for solidification for such alloys, in these cases you have the constitutional supercooling also occurs, and because of that you will have dendritic structures formed, and then that in that also you will have the coring developed. So, basically that is not a very much desirable structure. So, you go for the annealing of the cast structure, so that this chemical inhomogeneity which is there, that should be removed, and for that we do the chemical homogenization annealing. So, the purpose is through basically reduce this dendritic and cored structure to minimum, so that so when you do the annealing, so you are going to a temperature range where again at that temperature range there will be redistribution of atoms, the diffusion will be taking place, and basically that chemical inhomogeneity which is there throughout, so that will be minimized, so that you have the acceptable level of this coring which is acceptable for the application, that is observed. So, what is we do is, again here also you have to select one temperature and a time up to which there will be that will be kept under the slow cooling, and it will be kept at that temperature and then cooled, so that the proper diffusion takes place and the distribution of atom takes place, and the chemical inhomogeneity which is there, so that will be reduced. So, for if you look at the normal homogenization time, so for for typical nickel copper alloy, so nickel copper 30% alloy, it has been suggested that homogenization time is at about 6 hours at a temperature of say 1100 degrees centigrade, and so no, this is at 1000 degrees centigrade, and if you do it for 1100 degrees centigrade, so it will be at 1100 degrees centigrade, this time becomes only 1 hour. So, that such way if you increase the time, because the diffusion of atoms or diffusion rate is basically increased when you increase the temperature. So, that way your this chemical homogenization takes place, and the dendritic core structures, basically the extent of these coring, that reduces throughout the matrix. So, that is one of the principal heat treatment method in the case of non-ferrous metals and alloys. Another important process of heat treatment for the non-ferrous metals and alloys is the precipitation hardening. And as we know that in this case you have to have the alloys in such a manner that the solubility of one of the component is decreasing as the temperature is coming down, and mostly for aluminum copper system we have seen. So, again this is one of the method for the heat treatment which is very much widely used. We have already discussed about it, where we are again further heating it. So, first of all we are trying to have the supersaturated solution, and then we are going for the solution treating. We are again heating going into that range where the solubility becomes more, and then in that what we do is depending upon the temperature and the time, there will be nucleation of the precipitate. So, the second phase particle that basically will be coming up. So, basically so we have seen already that there are different stages. You have the coherent, there should be coherent interface. So, you will have the different stages. You have by the GP zone, and then you have the theta prime phase, and then you come to the equilibrium phase. So, as we see that as it moves to the GP zone theta prime, so you are getting the increase in properties, and after that once you increase the aging time or the temperature also. So, in that case there will be further growth. So, that will be reducing the properties. So, so in this case you have the processes which are followed is the solution treatment. So, so you will be allowing this specimen to be heated, so that what to ensure that the solute which is there, it is dissolved, because we are having a supersaturated solution. So, we are going into a temperature range where we feel that. So, because suppose you have if you look at the percentage of B in A is there on this line, and if such is the line, so this is your theta. So, this will be basically the alpha plus theta, and you have alpha here. So, you will be heating and going into this zone. So, this will be your heating point. So, the temperature will be raised up to this point, so that you go into this zone. So, that is and then you are keeping in here, because you are trying that and you are giving some time so that these precipitates they start coming out. Solution treating is that one, and then you will have the precipitates coming out. So, after you reach and ensure that all the solute is dissolved, you are basically cooling fast, and then further you are aging. So, you are heating to a lower temperature, and then further you are keeping either so certainly these the particles which are excess, so they will try to come up as you heat, or even naturally also it will take more time, but otherwise if you heat, then in a lesser time they start growing, and basically that the principle is that they impede the motion of the dislocation through the matrix. So, that way your strengthening is achieved. We have already studied that how there are methods that how the dislocation will either it will cut through the precipitate or it will bypass and it will move around. So, that way the main purpose is that you will have a mechanism by which the stress required to move the dislocation will go on increasing, will increase if a proper aging time and aging temperature is selected, and that way the strengthening is achieved. So, these are the different type of heat treatment methods for the non-ferrous metals and alloys. As we see that homogenization temperature treatment is used prior to mechanical processing of the cast ingot, and the temperature and times used depend on the diffusion rate and the starting structure. That was in the case of homogenization annealing. Similarly, you have another example, that was the precipitation hardening that we have already discussed. So, these are the different methods. Thank you very much.